Hey everyone, welcome to This Explainer. We're jumping right into the heart of scientific truth today. We're going to look at exactly how physicists take messy, totally unpredictable real-world data and somehow translate it into concrete universal laws. So let's start with a massive question to really frame this journey. You're in the lab, you've taken your measurements, you've got a whole list of numbers. But how much can you actually trust them? In physics, a number without a unit is pretty useless, sure, but a number without an uncertainty? That's literally just a guess. So how do we prove a law of nature is true when our human hands and our instruments are inherently flawed? To answer that, we're diving into this incredible source material, the official Cambridge International AS and A-Level Physics Comprehensive Study Booklet. Honestly, it's essentially the ultimate rulebook for advanced practical skills. It gives us the exact rules of the game for proving physical relationships in the lab, and we're going to break down its biggest secrets today. Here is our roadmap for the explainer. 1. The art of measurement. 2. Calculating experimental uncertainties. 3. Advanced instruments and analysis. 4. Visualizing data with graphs. And 5. Evaluating measurement results. Section 1. The art of measurement. The source text makes this absolutely foundational distinction right off the bat between accuracy and precision. We tend to toss those words around interchangeably in everyday life, but in the physics lab, they are completely different beasts. Accuracy is all about how close you are to the true value, and it gets ruined by systematic errors. Think of a ruler with a worn-down end that shifts every single reading by the exact same amount. Precision, on the other hand, is about the closeness of your repeated readings to each other. It's totally at the mercy of random errors, like the room temperature fluctuating, or just shaky hands. Picture a dartboard. If you throw a really tight cluster of darts, but they land way off in the top left corner, you are highly precise. I mean, your technique is incredibly consistent, but you're not accurate. A systematic error, maybe a bad stance, is totally throwing you off the true value. Conversely, if your darts are scattered all over the board but kind of average out to the center, you've got high random error. The ultimate goal for us physicists? Hit that tight cluster dead center. True precision, true accuracy. Section 2. Calculating experimental uncertainties. Since we know our measurements aren't perfect, we have to calculate the exact size of our inevitable flaws. The booklet lays out these specific mathematical rules for tracking propagating errors. When you combine measurements to calculate a final number, those errors stack up fast. If you're adding or subtracting values, like finding a change in temperature, you simply add their absolute uncertainties. But if you're multiplying or dividing, say dividing voltage by current to find resistance, you have to add their percentage uncertainties. And if you're raising a measurement to a power, like calculating volume from a length, you multiply that percentage uncertainty by the power. The error grows so fast if you aren't careful. And here is a wild fact from the text, 0.2 seconds. That is the average human reaction time. Turns out our biology makes us a completely terrible stopwatch. If you're manually timing a pendulum swing that takes 1 second, your built-in reaction time creates a massive 20% uncertainty right out of the gate. It is literally the biggest bottleneck in manual timing. Section 3. Advanced Instruments and Analysis. To defeat that massive human error, we really need to step up our game. Our first high-tech solution is the oscilloscope. When things happen way too fast for the human eye to track, like a rapid alternating current or capacitor discharging, we use this device to literally draw the voltage on a screen against time. But just plugging in an oscilloscope isn't enough. You have to know how to maximize its precision. The source material is super specific about this. You want to adjust the Y gain to stretch the waveform so it takes up most of the vertical screen. Why? Because making it bigger shrinks your relative reading error. And then you adjust the time base horizontally so you can see several complete cycles at once. Just like timing 20 pendulum swings instead of 1 reduces your percentage uncertainty, measuring across multiple waves on the screen drastically sharpens up your data. But what about tracking moving objects? Well, by using a light gate hooked up to a data logger, you completely bypass the human nervous system. The moment a moving object breaks that infrared beam, the computer logs it. You instantly eliminate that pesky 0.2-second biological delay we just talked about. It makes your speed measurements unbelievably precise and lets you capture high-frequency samples a human could never pull off. Section 4. Visualizing data with graphs. Once our advanced tools give us that highly precise data, we have to visualize it to actually spot the hidden trends. In the Cambridge Physics Lab, graphing is a rigid standard. You always put your independent variable, the one you control, on the x-axis. Your scale needs to be simple and stretch across more than half the grid. But the real art form? Drawing a perfectly balanced, razor-thin line of best fit. You want to balance your points evenly above and below that line, and crucially, you need to actively hunt for anomalies. Find those outliers, circle them, and boldly ignore them when you draw your line. Now, here's a common trap: calculating the gradient using raw data points. Raw data is full of random error. Instead, you want to draw a massive gradient triangle spanning at least half the length of your line of best fit. You read the coordinates directly from that perfectly smooth line, effectively averaging out the messy reality of your raw data to uncover the true mathematical constant. But what if nature doesn't give you a straight line? What if your physical law is some exponential curve? We can actually use mathematical judo to force a curve into a straight line using logarithms. If you have a law like y equals k times x to the power of n, you just take the log of both sides. It magically rearranges into the standard straight line format, y equals mx plus c. Plot log y against log x, and boom, your gradient reveals the hidden power n, and your y-intercept unmasks the constant k. It's basically reverse engineering reality. Section 5. Evaluating measurement results. This is the climax of the scientist's journey. This is where we mathematically prove if the experiment was a success or a total failure. When it's time to make the call, you step rigorously through this exact protocol. Let's say you're testing a constant, k. You calculate k from two totally independent data sets. You propagate your uncertainties to find the percentage error for both. Then you calculate the percentage difference between your two k values. The golden rule here: if the percentage difference between your constants is less than or equal to the sum of their percentage uncertainties, your physical relationship is solid. Your tracked errors perfectly explain that tiny gap in your math. And if you're relying on a graph, one beautiful line of best fit just doesn't cut it. You have to prove exactly how far off your gradient could realistically be. You draw error bars on your points, and then draw the steepest acceptable line and the shallowest acceptable line that still fit inside those error bars. Comparing those worst fit lines to your best fit line gives you the exact absolute uncertainty of your gradient. You're literally putting strict mathematical boundaries on the truth. We finish up with an absolute insider secret from the Cambridge Handbook. This is exactly how an examiner expects you to write your final conclusion. You don't just write human error or my equipment was bad. You have to be highly specific and use these exact templates. Seeing this perfectly phrased conclusion really anchors the whole goal. Quote, the percentage difference between the two values of k is 2.3%, which is less than the sum of their percentage uncertainties, 5.1%. Therefore, the relationship is supported with an experimental accuracy. Writing this proves that our carefully calculated errors fully account for the messy reality of the experiment. We've proven the law, despite our flawed human hands. So the next time you drop a ball, measure a voltage, or swing a pendulum, think about this. From fighting a tiny 0.2-second manual reaction time, to drawing worst fit lines, to calculating the propagation of absolute errors, ask yourself, how does hunting down these microscopic, seemingly tedious uncertainties ultimately unlock the massive fundamental laws of nature around us? Because without this rigorous quest for precision, we really wouldn't know anything about our universe at all. Thanks for joining me on this explainer, and keep questioning the data.